Welcome to day 2 of our embedded system course. In the previous session, we discussed what embedded system is and where they are used and also difference between C and embedded C. We saw that embedded systems are all around us in household devices, vehicles, industrial systems and many other things. Today, we are going to understand something very important. Once we write a program, what actually happens to that code? Because writing code is only the first step, right? The program doesn't directly run inside the microcontroller. It has to go through a process before the hardware can understand it. That complete process, what we will be discussing today. Okay. So, in this session, we'll focus on these three topics: how a C program is built, how source code becomes a machine code, and the difference between compiler and interrupter. These are basic but very important concepts. Before we start working with LEDs, sensors, and also the communication modules, we need to know how our code reaches the hardware, because whenever we write an embedded system application, there is always a process happening in the background. Okay, let's think about a simple example. Suppose you open an system and write a C program. You may write some variables, loop, conditions, maybe a function also, right? You save that file. Now, can that file directly run inside the controller? The answer is no, because the code we write is written in a language that humans understand, right? We use words, symbols, variables, and functions. But the processor inside the controller does not understand these words. Like, for example, int main. It won't understand what int main means. Return 0 we have written in the last, so it won't understand what that return 0 do. Okay, it only understands binary instructions like zeros and ones. So these must be some conversation process. That conversation process is called the build process. You can think of it as translating our human readable code into a hardware readable instructions. Okay, so the first step is creating a source file. When we write a program in C language, we save it with .c extension. That file is called source file. For example, suppose we write int main printf bracket opens hello world bracket close and semicolon return 0. Or one more example like int a equals 10, a plus 1 is 11. This code looks simple to us. Okay, we can read it immediately, we can understand the code where we are creating a variable and incrementing it and bringing that output and printing in the console. Okay, but for the processor, this statement has no meaning at all. Okay, the processor does not understand the word int or the variable which is a. Okay, it only understands low level instructions. So the .c file enters the build process. Okay, so when we create a .c file, it goes to one more process called compilation, then linking happens and an hex file is generated. Then that file will be flashing to the MCU and that will get executed. So when the code is executed, we'll get the output like this. Okay, so this is the process which we'll be going. Now next I'll be teaching you each and every step what it's going to do and how it is making the difference. Intentionally, I have hidden the free resources. So to get today's PPT and the free resources, please join our Telegram group. The link will be given in the description box. Okay. So the first step of this build process is pre-processing. Okay. Before the actual compilation starts, the preprocessor checks the special instructions in the program. These are called preprocessor directives. Like, for example, we can say hash include or hash define words are there, no? So those are called as pre-processing. Suppose we write hash define pi, which is the pi value is 3.14, right? Here the pi is just a symbolic name for that 3.14 number. The preprocessor replaces every occurrence of pi with 3.14. Similarly, we include a header file like hash include stdio.h, correct? So that what that mean is the standard input and output files, the header files. I can say example of the printf thing which we use in our code, right? That word, its internal library function will be written in the stdio.h file. So if we include that whole folder, we can use the functions inside that libraries. The preprocessor, what it does, it inserts its content into the program. So this stage prepares the source code for further processing. You can think of a preprocessor as cleaning and arranging the program before the conversion begins. Okay, this is what preprocessing does. Next comes compilation. This is where the actual source code is translated into an assembly code. At the same time, the compiler checks whether the program is written correctly or not. For example, if there is a missing of semicolons or undeclared variables, syntax errors and all will be there, no? So that will be detected in this process. If the program contains any error, compilation will be stopped. That means the next stage cannot happen. This is why compiler messages are very important. When you start practical embedded programming, many of your mistakes will first be detected during the compilation process. For example, suppose we can take as int a equals 10. Okay, I'll miss that semicolon. What the compiler will do? It will stop the process itself. Okay, so compilation means converting our normal code to an assembly level code. Example is given in the slide. So here we have our normal code written. Okay, so the compiler, what it does, it is converts this normal code into an assembly instruction which is given in the right side block. Okay, this is what compilation mean. For today's PPT and free resources, please join our Telegram group. The link will be given in the description box. So our next step is assembly language. This is much closer to processor instructions. Okay, for example, we have our assembly code, right? This move r0 comma hash 10. So this move means moving the data, add means addition, like doing addition operation, and also r0 is register. It's a register where the values will be going in storing. Okay, registers are very small memory location inside the processor used for temporary operations. Okay, so what happens here? Our machine readable language code was converted into a processor's instructions. That is the work of the compiler. Okay. In assembly stage, this step converts the assembly level language to an object code. So here we have the assembly level code, okay, which is move r0 hash 10 add r0 comma r0 comma hash 1. Means what this is doing is the previous slide which we saw, no, this one, int a equals 10 and a is incremented by 1 and it is placed in a itself. Okay, so now a value is 11. Similarly, this code means is we are assigning 10 to the register r0 and we are adding 1 to that r0 and that value we are storing into r0 only. Okay, this is the simple meaning of this assembly code. Okay, so this is converted and made into an object file. So object code is already a machine code, but it is not the final process yet. It is usually saved as an .o file. This file contains binary instructions, but it may still be incomplete because it may depend on other files and libraries. So one more stage is required. Okay, so on the left side you can see the assembly code, on the right side you can see the machine code. Okay, after assembly stage we'll be going to linking stage. Suppose your program uses some built-in functions, for example printf as I mentioned earlier, or the math functions or the startup functions. These are not fully written in your source code itself. They come from libraries. The linker's task is takes your object file and combines it with the required files or like required library files. For example, we have our main code. Okay, in main.o we have written our code and this scanner.o is having the library file. This is the library file. Okay, combining these together is the task which will be done by the linker. Okay, without the linking the program may compile successfully but still it is not completed. Okay, after linking the final output is generated. Okay, so in computer application this may be like .exe file which is executable file, but in the embedded system the final output will is usually .hex file or .bin file. These files contains machine instructions. This is the actual program file that gets loaded into the controller. So even though we wrote .c, the controller finally reaches the .hex or .bin file. Next comes the flashing process. Once the hex file is created, the next step is flashing. Flashing means loading the program into the flash memory for the controller. This is done using a programmer or a development board tool. Once the file is written, it remains stored in the memory. When the power is turned on, the controller reads these instructions and starts executing it. Okay, so here is a slide which will easily tell you what all files is generated in each process. So our first process is a pre-processing, right? In that process the .c file which we created will be converted to .i file. In compilation process the .i file is converted to .hes file. In assembly stage the .hes file is converted to object file which is .o file, and while linking the .o file is converted to hex file or the executable file. Okay, so this is the complete process which will be happening in every stage. Like everything starts from the code we write. Okay, from source code till the last machine code generated. This is the process which we will be following. This is no matter how simple or complex your project is, but this every code will be going through this process all the time. Intentionally, I have hidden the free resources. So to get today's PPT and our free resource, please go and join our Telegram group. The link will be given in the description box. Now, the next question is, who converts the program? Like, I have explained you the complete build process now. Who is doing all these things? Right. There are two methods to do this. One is compiler and one more is interrupter. Both work is to convert the code, but their working method is different. If you take a compiler converts the complete program at once. It reads the whole program first, then generates the machine code. C uses compiler based translation. This is why C is widely used in embedded system. It gives effective code and a good performance. Okay, and interrupters work is different. It reads one statement at a time and executes it. Okay, then moves the next statement. This means execution happens line by line. It is useful for testing and scripting, but execution is slower compared to a compiler. The Python is commonly explained using the interrupter based execution. Okay, in Python we use the interrupter based, but in embedded C we use the compiler based thing. Now, a simple way to remember this is compiler is like translating an entire book first and then reading it. Okay. Interrupter, what it does, it's like translating each sentence while reading. That's the key difference we can say. Embedded system prefers compiler because performance and memory efficiency is very important in our code. Okay. So today's session we understood what happens after we write a code, right? We learned how source file is converted step by step into a machine instructions. We saw the build process, which is pre-processing, compilation, assembly, linking, hex file generation and flashing the code. And finally, we learned the difference between compiler and interrupter. Okay, so I hope you all had understood it very well. I have made it very easy for you all to understand it, like in our common words, so that you can remember it. If you have not watched our day one video, please go and watch that.